Hello dear students, welcome to the online lecture series of design of steel structure. In today's lecture, we will be learning the design of laterally unsupported beams. There are the situation where the beams girders have no lateral support over a brace or a bracing over a part or a whole of the span. For example, gantry girder. For such laterally unsupported and unbraced beam, the compression flange may buckle sideways, causing the lateral torsional buckling. Dear friends, laterally unsupported beams means what? Beams having a larger span and the top compression flange is not supported. That is, it is not embedded into the concrete. As it is not embedded into the concrete, it will be causing a lateral torsion buckling for the beam. Those beams are called as laterally unsupported beams. Situations for the laterally supports beam. First, bending is about the major axis of the section. Second, the section is hollow or a solid bars. Third, in the case of major axis bending, where alpha LT is less than 0.4. The design bending strength for laterally unsupported beam as governed by the torsional buckling is given by MD is equals to beta B into ZP into FBD. Here beta B is equals to 1 for the plastic and the compact section, whereas for the semi-compact section it is equals to the ratio of ZE by the ZP, where ZP and ZP are the plastic section modulus and the elastic section modulus with respect to the extreme compression fiber, and FBD is equals to design bending compressive stress obtained as given. See table number 13A and 13B. Here FBD is equals to xi LT Fy divided by gamma m0, whereas xi LT is nothing but the bending stress reduction factor to account the lateral torsional buckling, and it is calculated by xi LT is equals to 1 upon phi LT plus under root plus into bracket phi LT square minus lambda LT square bracket raised to 0.5, and it should be less than 1. Whereas again phi LT is having its another formula. It is equals to 0.5 into bracket 1 plus alpha LT into bracket lambda LT minus 0.2 plus lambda LT is a square, whereas lambda LT alpha LT is the imperfection parameter which is given as 0.21 for the rolled steel section and 0.49 for the welded steel section. If the section is rolled steel section, that time we take alpha LT as 0.21, whereas in the case of built up section or welded steel section, alpha LT is equals to 0.49. The non-dimensional slenderness ratio alpha LT is given by alpha LT is equals to under root of beta B ZP Fy upon MCR, and this should be less than under root of 1.2 ZE Fy upon MCR, which is alpha LT is also equals to under root of Fy upon FCRB, whereas MCR is the elastic critical moment calculated in the according to the 8.2.2.1 of IS 800 2007, and FCRB is nothing but the extreme fiber bending compressive stress, and it is calculated by using the interpolation. Now, in the case of simply supported prismatic member with symmetric cross section, the elastic lateral buckling MCR can be determined from MCR is equals to square root of pi square EY upon LLT square into bracket G into I plus pi square EIW upon LLT square bracket complete, which is equals to beta B ZP into FCRB. Beta B ZP FCRB, whereas FCRB of a non-slender rolled steel section in the above equation may be approximately calculated from the value from the table number 14, which has been prepared using the following equation. We can either calculate FCRB by interpolation or directly calculate FCRB by using this formula. I have highlighted the formula in the slide. We may refer table number 14 for FCRB, but before referring table number 14, we need to calculate FBD from table number 13A and 13B, which are on page number 55 and 56 respectively. Dear students, we have two different methods to calculate this FCRB. FCRB directly can be calculated by using the formula, or it can be calculated by interpolation method. The following simplified equation is used to calculate the MCRB. MCR is equals to pi square EY HF upon 2 LT square into bracket 1 plus 1 upon 20 into bracket LLT upon RY upon HF upon TF square bracket raised to 0.5, where IT is the torsional constant for open section, IW is a warping constant, IY and RY are the moment of inertia and radius of gyration respectively about the weaker axis. LLT is the effective length for the torsional buckling. If you see table number 8.3, you will be getting the effective length for the torsional buckling of a section. HF is nothing but the center to the center distance between the flanges, and TF is thickness of the flange. Hence, MCRB for the different beam sections, considering the loading, support conditions and non-symmetric section, shall be more accurately calculated using the method given in the annexure E. Dear student, as I have described previously how to calculate the effective length for the lateral torsional buckling. See here, for the beams, girders of a span L where no lateral restraint to the compression flange is provided, but the end is restrained against the torsion, the effective length LTT of a lateral buckling is given as. Here are the effective length for the normal loading. These are the lengths for the destabilizing loading. If you observe the table, the first column is of serial number. The second column is again divided into two sub-columns, torsional restraint and warping restraint. The third column is again divided into two types, normal and destabilizing. Here, whenever both the flange, see here, dear students, here it is fully restrained and the warping restraint is both the flange are fully restrained. The beam will be restrained against the torsion and warping as that of our effective length for the column. There we are considering the column is restrained against rotation and translation. Here we are considering the beam is restrained against torsion and warping. When the beam is fully restrained against torsional and both the flanges are fully restrained against warping. For the normal loading, the effective length is 0.7 L. When the beam is fully restrained against torsion and only the top compression flange, here friends, top compression flange are fully restrained. In that case, for the normal loading, the effective length is 0.7 L. Then we come to the case number 4, that when the beam is fully restrained against torsion but the compression flange is partially restrained. I am always saying that top compression flange because the compression is at the top of the section. In that case, for the normal loading, the effective length is 0.85 L. When the beam is fully restrained against the rotation and warping not restrained in both the flange. Here if you see case number 1, warping is fully restrained in both the flange. Here in this case, warping is not restrained in both the flange. That time for the normal loading, the effective length is 1 L. Now from this sixth condition, the beam is partially restrained at the bottom flange for the support connection and the warping not restrained in both the flange. That time dear student, we have to take here the effective length as 1 L plus 2 times the D. And in the last case, whereas torque partially restrained by the bottom flange bearing support and warping does not restrain in both the flange, the loading condition is normal and the effective length is 1.2 L plus 2D. Note that torsional restraint prevents against the rotation about the longitudinal axis. If at all, in the numerical, to confuse you, they may also give the beam is fully restrained against the rotation. That time you may observe, you must know that the beam is fully restrained against the torsion. Then the warping restraint prevents the rotation of the beam in its plane. It may be also given that both the flanges are fully restrained in a rotation of the flange in its plane. That time you must note that the beams are restrained against the warping, and whatever the D which we have utilized in case number 6 and case number 7 is nothing but the overall depth of the beam. This 1 L plus 2D is the overall depth of the beam. So hence, dear students, we have designed our laterally unsupported beam. These are the design steps. In the next lecture, we will be learning the numerical on it. I will be solving numerical by using both the method, by using the interpolation method as well as by using the formulas. So till then, keep watching and subscribe the channel. Thank you.